Hi everyone, my name is Hila Zohar. I'm super excited to be here in the Women on Stage Global Virtual Conference. So today I'm going to talk about NLP, its past, present, and future. And we're going to start by explaining what is NLP. So NLP is an acronym for Natural Language Processing, and it's basically about making computers do something intelligent with language. It can also be seen as a field in the intersection between computer science and linguistics. When it comes to choosing NLP tasks, there are so many. Basically, any sort of interface between humans and technology has an NLP component to it, as humans primarily interact using language. But I've highlighted a few prominent ones. Text classification is the first one. Very basic, very useful. Given a collection of text, you need to classify it to one or more predefined classes, such as emails as spam or non-spam, comments as toxic or non-toxic, etc. Text generation. Given a sort of text prefix, you need to complete the text based on the prefix. That's sort of like similar to ChatGPT, we'll get to that, but that's a sort of flavor of natural language generation. Information extraction, also very useful. So text basically is a lot of unstructured data, let's say. There's no structure, you can't really put it instead of like columns in a database. So information extraction allows us to move from this unstructured big pile of text into some structure with information about it. Machine translation, also super useful. Google Translate, we always use it, and is a core NLP task. Spelling correction, also very useful. Works super well in English, still working on it in other languages, and also very useful. When it comes to NLP timeline and milestones, so basically NLP has been around for decades and decades, since the 1950s of the past century, where it was basically for about 40 years, it was about encoding language structure using rules. Okay, so when we learn a new language, we usually start by learning the rules of using it. It's grammar. So this is something that can be transferred to a computer manually by handwritten rules. In the 1990s, with the surge of the World Wide Web and the internet, a lot of text was made digitally available, so we could run statistical models on it. Then in the 2000s, the first sort of idea of neural language models, which means when we train a neural network on the task of predicting the next word given its prefix, the network learns something about language. We'll get to that. That was in 2003 already, Bengio et al. And also the idea of moving words to a sort of a distributed representation, which means just a big vector that represents this word. This, of course, helps the computer understand, since in the end, the computer understands bits and bytes and numbers. 2013 to 2017, the word Tevek, glove papers, RNN, LSTM. If you're not sure and it sounds like Chinese, don't be afraid, we'll get to that in a few slides. 2017, a seminal paper called Attention is All You Need, or the Transformer paper, came out. And from then on, the sort of boom of large language models, GPT and all its versions, and a contextual word representation using BERT, Elmo, etc. And 2023 onwards, we're heavily using LLMs in NLP for most things, for some we don't, and the future seems very bright. So let's sort of zoom in and start thinking about how do we do NLP. and we're gonna frame it using these sort of timelines that we saw before. So one disclaimer, of course, it's not like if 2000s finished we stop doing NLP like this. This is just highlighting the prevalent ways that we do NLP according to what was available, but of course you can mix and match, and sometimes you still use sort of old methods for certain tasks. So in that time frame, the prevalent way to do NLP was basically given we have a task, we have a classification task, for example, like we did before with the spams, the comments, we have a translation task. So basically, let's take the translation task. You basically had a collection of corpus in the source language, let's say in English, and then its translation for each sort of document or sentence, you had its translation in the target language. So once you had that labeled data, what you did was sort of infuse the machine learning model with linguistic knowledge, because basically back then we had to really the sort of modeling that we had and the amount of compute and the predictive power of the models that we use, such as SVM, naive Bayes. For translation, it was more like CRF and HMM, which are more like sequence-based models. The models themselves didn't have that much knowledge going on within themselves, so we as humans had to infuse the knowledge. So it was a lot about feature engineering and how do I understand the task and what do I think will help the machine do translation better, classification better, be it, let's take the spam idea of classification, what sort of I would need to do a lot of feature discovery and analysis and try to understand what makes an email a spam email as opposed to a non-spam, whether be it the length of the text, a certain URL, markups, cap locks, etc. So this knowledge is basically needs to be transferred to the machine, and we do that by using a lot of sort of annotations and pre-processing on the text. Some tasks needed sort of a more deeper understanding of language, so we would run a dependency parse, which is sort of trying to break up the sentence into its subject, objects, etc. So again, a lot of domain knowledge needed, a lot of hand-labeled data, and the sort of the machine learnings we had, models we had then were sort of good, but not as good as we'll see later. So sort of in 2000s, we already started using, some people started using deep learning, but the big boom happened in 2013 and 14. And the biggest enablement to it was basically the Word2Vec and the glove papers, which sort of really gave us a way to move from a sequence of characters into a meaning. So from a word to its meaning. So that meant basically that we were inside some sort of an embedding space. And what does that mean? So let's go back to the 1950s. A linguist named Firth said a word is characterized by the company it keeps. So this sort of makes sense to everyone, right? We learn the meaning of the word from its usage. So for example, let's look at this blue cube over here. The embedding space has this cluster of Java, C#, Python. All of these are similar words. There are programming languages. They are used in the language in a similar way. So in similar sentences, right? My Java code doesn't work. I have an infinite loop in my Python code. This is something that happens to everyone, and it happens in the same situations. So these words will appear in the similar cluster, and we also get nice things, properties from that space, which corresponds to semantic relations or analogies, like France to Paris is the same as London to UK. So this is already something really cool that the machine sort of knows right now, because we represented the words in that space. And then we can sort of leverage it to use deep learning, because we have a way to transform from this sequence of character to the sort of semantics of the word. So how did we do NLP with word embeddings? And also sort of with that, we sort of reclaimed and started using again RNNs, LSTMs, and getting much better results. So RNN is basically an unfolding network, a recursive neural network that sort of updates its weight according to the sequence and the outputs it's generating. So this is super useful for a lot of NLP tasks because it's sequence based. So basically, a sentence is a sequence. We can either generate one output at the end, which is sort of a classification task, or we can generate outputs continuously, sort of sequence to sequence, like translation. But these sort of methods, RNN, LSTM, etc., have two disadvantages. The first, it's quite slow to compute, because basically for RNN, you need to sort of process and update the entire sequence, and you can't really do the last sort of prediction until all the ones before you, sort of the units before you or the words before you finished their compute. So you can't parallelize it, right? Because you have to wait for everyone else to finish before you can output your prediction. So slow to compute. And the other thing is that basically the way we learn in neural networks, and this is sort of, for those who don't know, I'm gonna hand wave for a minute, so bear with me. So basically what we do with the neural network. So as we said, we have this labeled data, let's say emails with spam and non-spam. We represent the sentences using word embeddings, etc. And then we have the network, RNN, let's say, and then we're gonna predict a score for the email, like how likely is this email to be spam, and we say 0.8. But then we also have the gold label, like the actual truth, this email is not spam. So we need to sort of learn from our mistake, right? We made a mistake. We thought in 0.8, so 80% probability that this email is spam, but basically it's not. So we need to sort of learn and update our parameters because we made a mistake. So this sort of update procedure is called BERT propagation, and it's basically doing derivatives. So if you do a derivative over and over again, you will get to a sort of plateau of 0, which means you're basically not updating your weights and you're not learning anything, which is sort of missing the whole point of machine learning. So these two problems were sort of holding us back. And then came the amazing paper, Attention is All You Need, in 2017, and basically solved these two issues. So the first thing they solved is that you don't need to wait for the entire sequence. It's something that can be run in parallel. The architecture of the transformer of the Attention is All You Need paper means that you have these attention heads, and I'll explain attention in a second. But you can think you just have these separate units, and each one is doing its own processing, doing its own predictions, and then you don't need to wait, and you can just parallelize it and make basically better use of your GPUs and hardware. So that's the first thing. And the second thing is the BERT propagation is we're not doing the derivatives over and over again on the same input. So basically you don't have the vanishing gradient problem, and your learning is more powerful. So attention is basically, this example is a nice example of a dog. But the original paper was about neuro-machine translation. But I think visually this is nicer to see. So let's say we train a deep neural network to identify whether a dog appears in this image. So basically we can see that in the middle, this is sort of the attention weights. So this sort of, we see that when a network learns to predict a dog, it's gonna look for sort of the way these eyes look is very sort of dog-like, and the nose is sort of big and black, and the ear shape is pointed. So these are like the features that it learns that help it make a prediction that it is a dog. And these features are sort of saying, okay, also a human, like it's a dog wearing a human clothes, right? So this is like features that don't discern a dog from a human. So it sort of ignores this and pays attention to this, because this tells it it's a dog. So attention, you can think of it as just paying attention to the features that, or to the signals that help you be better at your task. So the transformer architecture was super useful and was used a year later for BERT and other contextual word embeddings. So what does BERT actually do? So BERT is like a huge transformer machine that was trained on mask language modeling, or you can also say it's basically a clause test. So a clause test, if you remember from your English lessons, is basically you had a bunch of text or even just independently sentences, and the teacher sort of had entire sentence and then sort of dropped one word and you had to fill out the word. So basically she was testing your knowledge of the English language, right? So the same here, we're sort of training BERT to succeed in this clause test, and then while we're training it, it's basically learning representations of words in their context in order to be better at this task. So what do we get from that? So if you remember, we had the word embedding space, but there actually each point in the space was one word. In BERT, we're gonna actually get one vector per word and context. So this is much richer and helps us sort of learn the ambiguity of the word and its contexts, and the representation itself is much more comprehensive. So let's look at the example here. Apologies for the morbid example. It's from the sort of the major paper of how to visualize and measure the geometry of BERT. So let's take the sequence of characters D-I-E. So D-I-E is D in German. It's a German article, so it's going to appear in a cluster here with the examples and the context. D-I-E is also die, so the verb of passing away. So it's going to have a cluster here. And also it's the singular of dice, so rolling a die is going to have a different cluster over here. So with BERT, we were able to actually move to another paradigm called pre-train and fine-tune. So basically, we were pre-training BERT, or usually using already a pre-trained one because it's massive transformer architecture and a lot of tokens. And we would take this sort of the BERT and we're gonna fine-tune it. So it means that we're gonna we can think of it like sending someone to university for doing one degree, and then switching to another major. You don't need to start from scratch. You just need to take a few courses. So sort of the pre-training is the big university days, like 3 years of sort of cramming knowledge, and then you just fine-tune. You just take a course or two for your specific needs. So that became sort of the way we did NLP, and we still do in most cases. But sort of in the same time, 2018, about a month after the BERT paper, came the first GPT paper. So already nice that you came to the talk, because for those who don't know, GPT is also an acronym for Generative Pre-trained Transformers. So we're gonna break up this three words and understand how they come together to be GPT. So generative, we already saw. Generative is the text generation task. So given a sort of prefix of text, I put touch is produced by, the model needs to predict the next word. So it's going to predict apple. Again, we're using sort of transformers, and we can predict the correct word. And then, so this is the generative, so language generation. Pre-trained is similar to the way BERT was pre-trained, so on a ton of text. And transformer, it's basically using the transformer architecture. So now you know what GPT stands for. So of course, over the years and over the releases, they've worked every time. Basically, every GPT version has a sort of accompanying paper that OpenAI sort of explain as much as they can what they did. So the first one, it was improving language understanding by generative pre-training. And then sort of in GPT-2, they already say it's multitask, they can do a lot of tasks. And then in GPT-3, they said it's few-shot learning or learners. How we trained the model was not only to predict the next word, but we did other things, which we'll get to in a second. So what did they do? So sort of, let's say, I'm going to explain here sort of GPT-3 plus, and also add another chat to it. So GPT and ChatGPT are not the same thing, okay? So basically the GPT-3 is sort of the language model, the base model that is useful for a lot of things, and ChatGPT is basically sort of fine-tuned in order to be sort of conversational agent. So what was different in sort of the 3 plus and the ChatGPT? So basically 3 building blocks. The first one was instruction or instruct GPT. This basically means that it's moving from, let's say, pre-trained language models is basically just taking tons and tons of text and sort of with transformers training it to predict the next word given the prefix, right? So this is pre-trained language models. Now, if we add instructions, we're basically augmenting this sort of free text training data with specific instructions, and it's going to look like, please summarize this document, and then I'm going to give it a document and a summary. So we're giving it sort of a mapping. It's learning a mapping sort of from the sort of concept or the word summarize and its actual realization. So just with language modeling on itself, it's not that easy to understand that summarize is basically something that's given a text and then it's summary. So if we do the instruction, it's much easier, it's much more compact, and the learning is made much more efficient if we spell it out. Same for programming code. So ChatGPT was trained on a lot of examples of, let's say, first, let's say, a sentence that said, please write me a code in Python that does backpropagation. And then we're gonna get the snippet of the Python code with the backpropagation. So again, we're moving from the sort of words of code in Python and backpropagation to its realization, to what it means. That's for the code. And another huge component is the reinforcement learning with human feedback. This means instead of giving, if in instructions the code I actually gave the summary or the code, in reinforcement learning with human feedback, I'm not gonna say the correct answer. I'm gonna give the machine a chance to produce its output, and then I'm gonna say this is correct or this is incorrect, and from that it's gonna learn. So this is much more efficient than doing sort of the instruction fine-tuning, but it has a disadvantage. It's very costly, you need humans there, the entire training process, etc. So how do we do NLP these days with if we have this ChatGPT and GPT? So there's this funny meme over here. But seriously, we use it a lot. LLMs are super powerful. They come to extraordinary results with little to no supervision. But there are still use cases where specific industry companies need something more tailored to them, or don't have this. They have scale issues. They have budget issues, security. There's still stuff going on also with LLMs with grounding, faithfulness, explainability. So some industry practitioners will only use LLMs, and some will still do the fine-tune and pre-train of BERT. So here's the future. Here's to the future. So here are some directions that are sort of already starting to take place and are sort of needed in order to bring us to the next level. So multimodal learning is already happening, sort of infusing the text also with signals from audio, acoustics, and vision. So this is sort of more holistic in the sense that humans perceive the world and communicate not just with language, but nonverbal cues and understanding sort of images. Another thing is that these models are huge. You saw the amount of tokens and parameters GPT needs. So we want to be more efficient for various reasons. And so that's another direction. Explainability is super crucial. As we move to the sort of AI first era, we leave a lot of decisions to the AI or sort of with it. So we really need a way to sort of open the black box and understand what's going on and understand why LLMs gave that prediction or that sentence. So currently that's very hard to do and is an active research area. And also one last thing, as we said, GPT was trained on tons and tons and tons of data, and also sort of instructions data and code data. And this is it's a very data hungry model. So another research area is how to make these models less data hungry. There are several problems that it's trying to solve. So the first is basically, if you want the GPT and this entire progress to happen not only in English, it's very hard right now because there is no amount of text available that is as large as English. Another thing, also programming languages, right? There are sort of English words in a sense, so that's already a problem. And also the other thing is that humans, we don't need that many to read that much, to absorb that much in order to perform tasks. So we're also wanting to align that. And there are tons and tons and tons of other directions as well. But our time is up. So I hope you enjoyed the talk and you've seen how NLP is involved from the linguistic rules of the 1950s to the ChatGPT giants of today. And of course, please do stay in touch. This is my LinkedIn, my email, and I hope to see you soon.